What if I wanted to find, say, do I like this pen? I think I like this pen. Limit as x approaches 3 from the right of, let's make it fun, the square root of, sure, 5x times the absolute value of x minus 3 over x minus 3, not an absolute value, sorry. Looks like it could look better, but that's all right. So, a limit like this, and we're also going to do the left-hand limit as well. To do a limit like this, you really have to know how to handle the absolute value. Specifically, we have to know this. The absolute value of x minus 3 is equal to 2 different pieces because it's really part of a piecewise function. It's interesting. I got some real interesting lag here. It's equal to just the insides if the insides are already positive. But that's only part of the time, right? X isn't always bigger than 3, because that's what that really says, right? X minus 3 greater than 0. That's just another way of writing x is bigger than 3. But if x is less than 3, or if x minus 3 is less than 0, well, then the absolute value of x minus 3 isn't x minus 3. And what if x was 1? 1 minus 3 is negative 2, and the absolute value of negative 2 is positive 2. We can't just write x minus 3 here. We need negative x minus 3. Because now if x is 1, 1 minus 3 is negative 2, and negative 2 is positive 2. So this is always how an absolute value kind of works. It's whatever you've got inside, if the insides are already positive, it's the negative of what you have inside if the insides are already negative to turn that negative into a positive. So if we're approaching 3 from the right, we're bigger than 3. If we're bigger than 3, we get to use this piece of the function. So for this first part of this limit, we do just get to say, I'm going to drop the absolute values. This is going to equal the square root of 5x times x minus 3 over x minus 3. And then, as is typical, we can cancel the x minus 3s or whatever cancels. So that's going to cancel with that. We're going to be left with the limit as x approaches 3 from the right of the square root of 5x. And then we just substitute in 3 for x and get the square root of 15. Point of interest, or I don't know, thing to remember, until you actually substitute in x equal to whatever x is approaching, you should be writing the limit in each step. And because this really means something. If you don't write this, sorry, I should be pointing somewhere everyone can see. If you don't write this limit part here, all you're saying is you've got some expression. It's an expression, right? It's a function, whatever. But when you see that there, that means something. That means, oh, what is this doing as x is getting closer and closer to 3? So it's very important to have that each time, right? If you just wrote that, it wouldn't mean the same thing anymore. So in this step, we also need to write that in this step. And then finally, in this next step, we say, oh, there's the answer to the question. As x is getting closer and closer to 3, this expression is getting closer and closer to the square root of 15. Let's look at the left-hand side, or the left-hand limit. Limit as x approaches 3 from the left of the same exact expression. Okay, well, things are going to be a little bit different. And here's what I would say in general about absolute value limits. Probably 99.9% of the time, they don't exist. Because almost all the time, when you have an absolute value in your limit, the left side and the right side don't end up matching up. That is very, very, very typical. I feel like I need to zoom out just a tiny bit. Oh, I know that I need to do that. Move this up here. Cool. Hope that's a little better. So in this case, still writing the limit as x approaches 3 from the left, square root of 5x. But now the absolute value of x minus 3, well, since x is less than 3, the absolute value of x minus 3 is negative x minus 3. And then when we cancel the x minus 3s, we're still left with a -1 multiple. So we end up getting the limit as x approaches 3 from the left of a -1 times the square root of 5x. And then when we substitute in 3, we're going to get negative the square root of 15. And those are not the same. So each one-sided limit definitely exists, but the overall limit as x approaches 3 does not. So we can then say the limit as x approaches 3 overall of the square root of 5x times the absolute value of x minus 3 over x minus 3 does not exist. And that's a pretty typical result when you're talking about absolute values, is that each one-sided limit does exist, the overall limit does not. There's so many different directions to go. Questions about this? Yeah.
Does the limit usually just not exist like when it's the point on the graph that's like intersecting the x-axis, or like if it was a different point, would it not exist on both sides?
I guess I'm not sure what you mean, like specifically like
because I'm just thinking on the graph I don't see why any point other than the one that's on the x-axis the limit wouldn't exist, because wouldn't it be the same on both the left and right side?
for any other point?
Yeah.
Yeah, for sure.
Oh.
Now I wouldn't necessarily say, I mean, I guess I'm not sure where the x-axis is coming into play here.
Because I'm just thinking the point where the graph changes direction is usually off of. But I guess it wouldn't always be on that.
Right. I mean, like if just to, I mean, I don't actually know what this graph looks like, but we can find out. So let's see, we want to graph y equal to, what do they make up here? The square root of 5x times the absolute value of x minus 3. Absolute value, I think you can just write ABS. Yeah, maybe not. Nope. Or I can just be smarter and just actually write the vertical symbols there. Yeah, that's right. And then divided by x minus 3. And you don't, I mean, this square root of 5x is in the numerator. This is written correctly. So, I mean, and then here's kind of the issue part, right? X equal to 3. So, I mean, I don't think of that as really being on the x-axis.
Yeah, I just imagined it in my head.
Sure, totally. That's totally fine. But we can definitely see, right, that as the x values approach 3 from the left, we're getting closer and closer and closer to the negative square root of 15. And as we approach 3 from the right, we're getting closer and closer and closer and closer to the positive square root of 15. And totally, as we approach 3, right, the limit is not existing because the left and the right side are clearly not matching up. So also, just in general, great tool to use, right? If you are not sure what this thing looks like, you can totally graph it on Desmos and see what it looks like and see, oh yeah, the limit doesn't exist. What do we do if a limit is indeterminate? What if the absolute value was on the bottom of the limit? So everything is being divided by the absolute value of x minus 3. So actually, if the absolute value was on the bottom, we'd end up with the same result. So just to point out, it's kind of, just to point out here. I like this being big. If we had the absolute value of x minus 3 on the bottom, it still ends up giving us the same sort of thing. This is still equal to 2 different pieces. It's x minus 3 over x minus 3 if x is greater than 3, which is just 1. I didn't do the square root of 5x part, just kind of point out what we have here. On the other hand, if x is less than 3, then we need the negative of what's inside the absolute value. That's just going to be -1 if x is less than 3. So it's still the same process whether or not the absolute value thing is in the numerator or the denominator. You're still just using this piecewise definition that take what you've got if the insides are positive, take the negative of what you've got if the insides are negative. And I guess I'm not sure really what your question about what if we do if the limit is indeterminate. This is an indeterminate limit, right? This is what if we started this one off, this is a 0/0 type, whether it's this one we're looking at here, like if I was doing like the limit as x approaches 3 of x minus 3 over the absolute value of x minus 3, this is an indeterminate limit. It's a 0/0 type. And so we would do, right, in this case, we're doing the left and right side. And really, I should say, when it's absolute value, you should immediately think, I probably need to look at both sides. But that's kind of always the thing we do with absolute values. Maybe not 100% of the time, but almost most of the time. And so looking back at this one, and this one was also an indeterminate form, right? You had an absolute value, or you had a 0/0 type, I should say. Hopefully that addresses that question there. And yeah. So I think we should get into this precise definition of limit stuff. I'm certainly happy to talk about other things. I know there may be some squeeze theorem stuff as well. Yeah, but I feel I'm kind of trying to think about which order it usually comes first, but let's do precise definition a little bit, and then maybe we'll get into the squeeze theorem later. Okay, so precise definition of a limit. Also known as proving a limit, also known as a delta epsilon. These all are words, different words for the same thing. So first, we really should get comfortable with some notation. So let's start off with this. We're going to sketch the portion of f of x equal to 2x plus 3, where, well, first we're going to look at where f of x in absolute value, so I should say the absolute value of f of x minus, let's see, what do I want here actually? Brain, sure. Sorry, I had one all like, sure, let's do that. F of x minus 7 is less than 1. We're just going to draw that. Okay, well, we don't have to draw this graph. And I should use multiple colors here. So let's see. 2x plus 3, I know how to draw that. It looks vaguely like this. And I know the y-intercept would be 3. I don't really care about that. But here's 7 right here. And I want to go 1 above and 1 below 7. Right? If I want f of x minus 7 to be less than 1, what I'm really looking at is f of x minus 7 between 1 and negative 1. And if I add 7 to everything, I'm looking for f of x to be between 6 and 8. So I'm looking at this portion of the graph right here. There's the portion of the graph where f of x is between 6 and 8, or where f of x minus 7 is between, sorry, f of x minus 7, the absolute value is less than 1. Everyone can see that, okay. And now we're going to do the same sort of thing, except, so we can keep this on screen here. So same graph, but now we want the portion where I'm sorry, brain. Oh, sorry, I just had a brain fart and it's killing me. Apologies. Yeah, we want to now plot the part where the absolute value of x minus 2 is less than 1/2. So but still on the same graph. So plot the same graph. about the same. And then what we're going to see here is that, so let's say x is about, let's say x is 2 right there. And that means I'm going to want x minus 2 to be less than 1/2, bigger than negative 1/2. Or if I add 2 to everything, 2.5 is 5/2. 2 minus 1/2 is 3/2. So I want x to be between 5/2 and 3/2. So I'm 1/2 to the right, 1/2 to the left. And even though my drawing isn't perfect, we're going 1/2 in every direction here. What I want to point out is these portions of the graph are actually the same. So let me say that again. Where x minus 2 is less than 1/2, and where f of x, minus 7 in absolute value is less than 1, these are the same portions of the graph. Oh, is this pen dying already? I don't know about these pens. Looks like there's still ink in there. I don't know about this. For purchase here. The graph y equal to 2x plus 3. Sorry, one sec. So, I mean, let's think about that. If x is, in fact, let's draw it over here. Oh, yep, sorry, thank you. Never hesitate to ask for that. Sometimes I forget that I have limited screen space here. So we're looking at the same piece of the graph. If x is 3/2, well, 2 times 3/2 is going to be 3 plus 3, which is 6. So that point there really does correspond to that y value there. And similarly, if x is 5/2, that's going to correspond to the y value being 8. So the thing that's really kind of important to see here is that if we're between or within 1/2 of x equal to 2, our function values are within 1 of the function equal to 6. Sorry, 7, apologies. Let me say that again. If our x values are within 1/2 of 2, our function values are within 1 of 7. But now, what if we want a smaller portion of the graph? Like, what if we really rather have, say, the portion of the graph where we're within 1/10 of 7? So what if we really want the portion of the graph where the absolute value of f of x minus 7 is less than 1/10? Can we find the number, and we're going to call it delta, so that the absolute value of x minus 2 less than delta describes the same portion? So graphically, we're looking at the same thing here. We're just narrowing our bounds. Sorry. So here's 7. We want to be as high as 7.1, as low as 6.9. And we're trying to find how far left and right of x we can actually do, of x equal to 2. Well, if we look back at the previous work, when we wanted to be 1 away from 7, we had to be 1/2 away from 2 for the x values. And the same sort of relationship is going to be true here. In fact, I was doing this in class during offsite earlier, and I kind of came up with something kind of neat. I think anyway. I know that essentially my slope of this line is 2. So for every 1 change in x, my y is going to change by twice that. Or for whatever change in y I need, my x is going to change by half that. So if I want to go from 7 to 7.1, I'm going up 0.1. Well, the x change needs to be half of that. It's going to be 2.05 or 2 1/20. Right? Some people like to write this as 7 1/10. This is going to be 2 1/20. So a change of 1/20 in x is going to equate to a change of 1/10 in y. Or essentially what we need to do here is we're going to do the math. So we want the absolute value of f of x minus 7 to be less than 1/10. Let's plug in what f of x is, which is 2x plus 3. And we might have lost that fact. Let's write it up here. So I'm at the absolute value of 2x plus 3 minus 7 less than 1/10. I'm going to simplify this. So 2x minus 4 less than 1/10. And then we're going to factor out the coefficient of x. And if it's positive, it's no problem. But I will warn you, here's what we're going to do really. I'm going to factor out a 2. And then when you take it out of the absolute value, you have to make it positive. So if it's already positive, no big deal. But if this was like a negative 3 times x minus 2, and I brought it out of the absolute value, it would become a positive 3. Essentially, what I'm really saying here is if you have an absolute value of a product, it is the product of the absolute values. Or here's the rule I'm actually referring to. The absolute value of A times B equals the absolute value of A times the absolute value of B. So if you bring something out of an absolute value, it has to stay positive. So this is going to be 2 times the absolute value of x minus 2 less than 1/10. And then we can divide both sides by 2 and get the absolute value of x minus 2. 1/10 divided by 2 is 1/20. So look, the function being within 1/10 of 7 is literally the same as x being within 1/20 of 2. That's the whole deal. And it's not the whole deal, but that's what we're trying to see here. Is we're trying to say we have this condition on how close we want to be to the value 7. And we can say, well, that means x needs to be this close to the value of 2. All right. So now, what if we want to generalize this? Oh, yeah, question, sorry.
Where did you get the x minus 2 is 1/7, or the absolute value of x minus 2 is less than 1/2 in the first place?
Sure. Well, so the real place I got it from was I knew what the answer was, and that was kind of the setup. But we could have done the same work. So to get, to get this here, we could have said, well, we wanted this. The absolute value of f of x minus 7 is less than 1. And then we could have done the absolute value of 2x plus 3 minus 7 is less than 1. And then the absolute value of 2x minus 4 is less than 1. And then the absolute value of 2 times x minus 2 is less than 1. And then, right? And then the absolute value of x minus 2 is less than 1/2. But the point of doing it this way was just to kind of show you that you can find the same portion of the graph by either thinking about a condition on the y's or a condition on the x's. And both this and this describe the same part of the graph. So you can say, oh, I need my y values to be within 1 of 7, or you can say I need my x values to be within 1/2 of 2. And either way, you are saying the same thing. And that's true if we want it to be 1, but we can also say, well, right, what if we really wanted our y values to be within 1/10? Well, then an equivalent way of saying that is saying we want our x values to be within 1/20 of the x portion. of the x coordinate. But now we want to generalize this and say, well, I don't really care what the number is. 1/10, 1/1000, 1/1,000,000,000. I want to know that if I need the function to be however close to 7, what should the corresponding condition on the x kind of parameter be? So here's the question. If we generalize and consider the absolute value of f of x minus 7 to be less than some epsilon. And when you hear epsilon, you should immediately think, oh, that's a small positive number. It doesn't have to be small, but you're usually thinking of it being small. Can we always find a corresponding number, delta, which is also positive, such that if the absolute value of x minus 3, or sorry, not if such that x minus 3 being less than delta describes the same part of the graph that's the question. Delta is also a small positive number. They're not necessarily the same, although they can be. So that's really the question. If you've got this function, minus 7, I should say, if the function is within epsilon of 7, can we find a delta so that x being within delta of 2 describes the same region? Graphically, here's what this looks like. It's really the same picture one more time. So all we're saying is that if we are within epsilon of 7, hopefully that picture is, you can see that, right? I can see that. Can we find delta so that x is within delta of 2? And the answer is definitely yes, a resounding yes. For this one, it's not terrible at all. In fact, we already kind of know what it's going to be, I think. We saw that for a value of 1, the x, like for an epsilon value of 1, x had to be within 1/2. And for the y values being within 1/10, the x values had to be within 1/20. It looks like the restriction on the x values is always half of the restriction on the y values. And that's totally the case here. So we can see that if we want the absolute value of f of x minus 7 to be less than epsilon, that's going to be equivalent to 2x plus 3 minus 7 less than epsilon absolute value. The absolute value of 2x minus 4 less than epsilon. 2 times the absolute value of x minus 2 less than epsilon. The absolute value of x minus 2 less than epsilon divided by 2. And that would be what we would say our delta was equal to. Well, that's a not great delta there. So whatever you pick for epsilon in this problem, delta has to be half of it. And again, this totally, for linear functions like this, it really is pretty easy to see because you can always think of the slope. And if the slope is 2 in this problem, which it is, for whatever change in x you're going to have, the y change is going to be twice that. So if we want the y, if we only want to be epsilon away from our y value, we only want to be half of that away from our x value because the slope is going to magnify that change by a factor of 2. Or you could even say, and this I thought, I won't lie, I kind of thought this was clever. You guys don't have to agree, but check this out. From here, if you're trying to end up with a maximum here, I'm going to go over and up, rise over run. My rise is epsilon, my run is delta, and epsilon over delta in this case has to equal the slope. So then, oh, look at that. Epsilon is 2 times delta. Delta is epsilon over 2. Pretty cool. Couple warnings about this. It really only works for lines. It doesn't work for other nonlinear functions. And if your slope is negative, you shouldn't have negative values in it. So I would just use this straight away, but it is kind of a neat observation to me. Okay. All right. So that's kind of the whole idea with these. I mean, it's not the whole idea, but it's kind of the basis of the idea here, that we can always find a corresponding delta for whatever epsilon. And if x is within delta of whatever x is getting closer to, then the function is within epsilon of whatever the function is getting closer to. And this is really the genesis of the idea for proving a limit. Because what our kind of goal here is, in fact, we're going to do it. This leads to the idea of a limit proof. So we want to prove the following. Prove the limit as x approaches 2 of 2x plus 3 equals 7. It seems pretty obvious, I feel like. I mean, not that it seems obvious, but that if someone said to evaluate this limit, it would be easy, right? You'd be like, I'm just going to throw 2 in for x and done. But proving a limit is a very different thing than evaluating one. So what does this limit really say? Well, I just want to remind you, what this says, all this says is that the function 2x plus 3, f of x equal to 2x plus 3 gets really close to 7 as x gets really close to 2. The thing that this proof does is it kind of codifies or makes you be really more specific about what you mean when you say really close. Right? Really close is not very specific. How close? 1/10, 1/10, 1/100, 1/1000, 1/1,000,000. The problem is you can always get a little bit closer. Right? No matter how close one number is to another, you can always find a closer number. And that's why we're doing this Delta-Epsilon thing, because what we're going to say is, well, if x gets within delta of number approaching, and then you can be like, we can all pick whatever delta we want, and we can make delta smaller and smaller and smaller and smaller. But if x is within delta of the number x is approaching, the function has to be within some other small value, epsilon, of the value it's approaching. Okay, so here's what we need to show. We need, in fact, so we need to show that for every epsilon that is positive, again, we're usually thinking of epsilon being small. It doesn't have to be small, but that's what we're thinking of it as being. There exists a delta, or I have to write a corresponding delta, also greater than 0, such that, and here's kind of the real meat of it, if the absolute value of x minus 3 is less than delta, I guess we should throw on a greater than 0 as well. X shouldn't be equal to 3, so we want to kind of exclude where x is actually 3. But if this is true, then the absolute value of f of x minus 7 is less than epsilon. When I see that, here's what I think. All that says, all this math says here, x is close to 3. That's all that says. It's a very mathy way of writing it, but it really just says x is close to 3. Or if you want to be a little bit more particular about it, it says the difference between x and 3 is smaller than a small number. But if we're saying the difference of two things is small, we're saying those things are close to each other. Yeah.
Wait, where did you get the x minus 3 from?
Oh, sorry, because I was looking at the wrong thing. I apologize. We want to be close to 2. Sorry about that. Holy smokes. Thank you. It's because I changed the example from the notes and then I read the wrong thing. Right, so if x is close to 2, then the function should be close to 7. So when I read this, opposite of x minus 2 less than delta, I'm really just saying x is close to 2. And similarly, what are we saying when we're saying that the opposite value of f of x minus 7 is less than epsilon? We're saying that exactly. That's all a limit means, right? As x is close to whatever x is getting close to, the function gets close to whatever the limit's supposed to be. That's all we mean when we talk about a limit. Okay, so how do we actually prove this? Well, the proof, we've really already done the work for the proof. We know that for this condition to be true, sorry, I keep pointing this thing, but there's people over here. We know that for this condition to be true, the x has to be within epsilon over 2 of 2. Right? That's what we found, that if this is less than epsilon, this delta has to equal epsilon over 2. All right, let's look back at all of our previous examples, right? We found, oh yeah, right, this had to be epsilon over 2. And all the differences for the x's were always half the differences for the y's. So here's our proof. And we usually try to make these very, very succinct. Your teacher might have a different kind of template for doing it, but here is what I have done in the past. Mine are, so yeah, I'm usually a little wordier than Grant, whose notes I'm looking at. So here is what I would say. For every epsilon greater than 0. Yeah, I really want to say more. So, but here's the very succinct proof, and then I'll talk about what I might say differently. If epsilon over 2 is what delta is equal to, then here's what we've got. The absolute value of f of x minus 7 is equal to the absolute value of 2x plus 3 minus 7, which is equal to 2 times the absolute value of x minus 2, which is less than 2 times, oops, sorry, epsilon over 2, which is equal to epsilon. Right, we did the work already. We know that x minus 2 is less than epsilon over 2. So we're seeing that if delta is equal to epsilon over 2, then f of x minus 7, the absolute value has to be less than epsilon. This proves the limit as x approaches 2 of 2x plus 3 equals 7. Now, usually we haven't done all the work beforehand, so our proof often is a little wordier than this, but this is the essence of the proof. All you really have to show is that if the x minus whatever is less than the appropriate thing, then the function minus the whatever absolute value is less than epsilon. That's the whole deal. Now, it gets harder if your function is not linear. Right? For lines, it's super straightforward. For not lines, a bit less so. Well, let's do another line example. Yeah. Okay, time flies. Actually, let's talk about kind of the very, very general format before we do an example. So to prove the limit as x approaches, you can either use x naught or a of f of x equals L. Yes, of course. We're going to say, first thing you want to do really is find what delta needs to be in terms of epsilon. That makes it true that both the absolute value of f of x minus L is less than epsilon, and the absolute value of x minus x naught is less than delta. And as I'm sure many of you have observed, this is what a lot of your homework's about. Right? A lot of you are finding this kind of stuff in your homework. Probably not everyone, because not everyone's in the same spot. And then 2, write the proof. And the proof typically goes something like, for any epsilon greater than 0, if delta is equal to whatever you found it to, then the absolute value of x minus x naught greater than 0 and less than delta implies, that's what that means there, that the absolute value of f of x minus L is less than epsilon. That is the most bare bones proof you can write for this. I usually write a few more words than that, but that's kind of the very essence of what you want. That's enough, right? That proves it. What that really says there is that if x is close to x naught, then the corresponding function has to be close to the limit. That's what all this mappiness says. Questions? We're going to do another example, but just want to see if there's any questions. Oh. This proof only works for lines. Exactly, Lauren. We're going to talk about, sorry, yeah. We're going to definitely talk about nonlinear functions in a moment. But yes, this type of proof specifically works for lines. We have to be a little bit more, what's our word? We have to be more careful when we have nonlinear things, but we will be. And it's not terrible. Well, it's not super terrible. It's a little terrible. Let's do another line one though. Let's say that we want to prove the following limits. Limit as x approaches -5 of 4x plus 2 equals whatever it equals, -18. We want to prove that limit. So typically when I do a proof like this, I break it down into two parts. First, I'm going to do kind of what I like to call my scratch work. This is kind of the not actually part of the proof work. Start with what you want. We know that we want the absolute value of the function minus the limit to be less than epsilon. So in this case, we want the absolute value of 4x. I want to make that negative. Oh well. Oh well. 4x. I'm going to change it to negative because I want to show you guys what happens if you have a negative coefficient. So let's make this a negative 4x, 20. Hate scratching things out. It's terrible. This is not that terrible. Sorry. There. Here's our new one. We're proving limit x equals -5 of -4x plus 2. Welcome. Let me see your symptom survey. So we want the absolute value of the function minus the limit, thank you, to be less than epsilon. And we're just going to solve. So now we know that we want this, but we also want the absolute value of x minus -5 to be less than delta. Right, those are the two things we want to go together. Well, this one is not terrible. It's x plus 5 delta. We need to work with this to get the same thing showing up over there. It's not hard when it's a line. And lines are going to be the nicest thing you can have. So I'm going to simplify and make the absolute value of -4x minus 20. And then what should I factor out from here? Right. So you got the absolute value of -4 times x plus 5 less than epsilon. And then here's the thing I was saying about negatives and absolute values. If you pull this -4 out, it has to be positive. So this is going to be +4 times the absolute value of x plus 5 less than epsilon. And then absolute value of x plus 5 is less than epsilon divided by 4. You should never be getting an epsilon divided by a negative number. That would be an issue because epsilon is positive and delta is supposed to be positive, and epsilon divided by a negative would be negative. So here's what we want. We're going to we want delta equal to epsilon over 4. Now we can write the proof. And I'm going to write a slightly wordier proof. So here's the proof I would write. So for any epsilon greater than 0, so when I was taught to do this, I was taught you should do 3 things. You should tell them what you're going to tell them. You should tell them what you told them. Really make sure they know. So the way I typically write this proof is I say, here's what we want to do. Here's what it is. We did the thing we done. I know it seems like maybe overkill, and you don't have to write all this, but this feels succinct to me. So here's what I'm going to say. For any epsilon greater than 0, we want to find a corresponding delta, which we just found, such that if the absolute value of x minus -5 is less than delta, then the absolute value of our function, negative 4x plus 22, negative 4x plus 2, minus 22 is less than epsilon. That's our job, right? I know we already did the job, but that was our scratch work, and now we're writing the proof. Tell them what you're going to do, or tell them what you're going to tell them, right? Here's what we want to do. We want to prove this thing. Now, here's the proof. Let delta equal epsilon over 4. Then it is true that the absolute value of x plus 5 less than epsilon over 4 is the same as, or implies that, the absolute value of negative 4x plus 2 minus 22 is less than epsilon.
Can you scooch it up a bit?
Yes. It's like there's noise coming from the computer. It's terrifying. But yes, of course. Now, sometimes here people show some of the algebra that they just did. Right? You could say, if you really wanted to, you could start with this and work backwards back up to that. I don't think that's required or necessary, but your teacher might feel differently about it. They might want you to be like, oh yeah, this, and then multiply both sides by 4, and then bring it in the absolute value and make it a negative 4, and then distribute it, and then break it apart. They might want you to show all that steps. I don't think they will, but sometimes they do. Finally, I would say something like, this proves the limit as x approaches negative 5 of negative 4x plus 2, holy smokes, is equal to, is equal to 22. Sometimes people get really lazy there and they just draw the little square thing and fill it in. That means you prove the thing you wanted to prove. This is probably more how I would write it, but you could probably get away with less. All right. So I want you all to take a crack at it. So here's what I want you all to try proving. The limit as x approaches 3 of 5x minus 1 is equal to 14. And I would encourage you to do the same sort of thing. Start with this. We want both of these things. The absolute value of 5x minus 1 minus 14 to be less than epsilon, and the absolute value of x minus 3 to be less than delta. So we want both of those things to be true at the same time. Work on this till you get to that. It's not a lot of steps. And then afterwards, try writing out a very similar proof, or right, you could also go with the less intense proof. But it's more like this. Can you get that on there? Can I fit all the things on the screen? Probably not. Yeah, I can't. Can't be done. Maybe. Sure. Good enough. Sorry, I want all the things on the screen, but I can't have everything. Can't I move this out of the way? Sure. So give yourself I'll give you 3-ish minutes to work on that. We'll walk around and look at things. Make sure you're not definitely should get delta and epsilon divided by 5. So we want this to be less than epsilon. Sorry, I gotta cover that part up. And we're always trying to get that if the those are the things we always want to be true. I will point out the lines, it's always going to be super easy to find for delta. It's always going to be epsilon divided by the absolute value of the slope. Slope is 5, the delta is going to be epsilon over 5. Slope is -6, your delta is going to be epsilon divided by +6. Super, I mean, it's not always super straightforward, but it's usually pretty not trouble to get there. And the work is just going to be, if I start with this, and if I just simplify this a little bit, you get the absolute value of 5x minus 15, less than epsilon, factor out the 5. 5 times absolute value of x minus 3 less than epsilon, and then divide by 5. Oh, yeah. That's our delta. If you want the absolute value of x minus 3 to be less than delta. That's usually the not terrible part. The terrible part is really just the writing it up. And it's kind of really, I mean, literally that's the same template I wrote when I was a student in 21A at UC Davis many, many years ago. I probably wrote that exact proof on a test. It hasn't changed, right? I mean, you could probably write something less. And really, I will say, if your teacher has a specific way they want you to do it, you should definitely do it that way, right? Don't do what I say, do what your teacher wants you to do. But if I was writing up this proof, I would say, okay, you want to start with for any epsilon greater than 0, we want to find, or you can just say we found it, yes, we already found it. We want to find a delta greater than 0 such that if the absolute value of x minus, let's see, x is approaching 3, less than delta, then the absolute value of f of x minus L is less than epsilon. I'm going to write a little bit more this time to show all the writing you could do. Let delta equal the thing we found delta to be, epsilon over 5. Then we can see that the absolute value of x minus 3 less than epsilon over 5 means that 5 times the absolute value of x minus 3 is less than epsilon, means that the absolute value of 5x minus 15 is less than epsilon, means that the absolute value of 5x minus 1 minus 14 is less than epsilon. But that's what we wanted, right? We literally just said we want to show that if this, then this. Well, we just did it. We showed that if this, then we got to this. That proves it. So some people are like square, I like to write thus. I like the word thus. Thus we have proved that the limit as x approaches 3 of 5x minus 1 equals 14. Because we showed the thing, right? We showed that if x is really, 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 really close to 3, then 5x minus 1 is really, really close to 14. So for example, right, if epsilon was, or if epsilon was, 1/1000th, and as long as x is within 1/5000th of 3, our function will be within 1/1000th of epsilon, or whatever small number you want to pick. All right. Let me open it up. Questions, comments, observations.
Explain again why when you do that fx minus L, but you subtract 14.
Well, because let me make sure I did it right. Like now we're gonna make a mistake. Okay, no.
I just don't understand why the output is what gets cut as L.
Well, so L is the limit, right? So we're trying to show that the limit of this function is 14. So that is what we call L, whatever the function is getting closer and closer to. If we graph this, 5x minus 1, and it looks kind of like this. Let's see, here's 3, and here's 14. What we're saying, right, is this function, f of x equal to 5x minus 1, as the x values get closer and closer and closer to 3, the y values, which is the limit, get closer and closer to 14.
Okay.
And what we're really saying with this notation here is that the difference between these two things is small. We're saying that this 5x minus 1, the function, is close to the limit 14 by saying that their difference is less than a really small number.
Okay.
And then I saw a hand over here. So, was Sophia?
Oh, I was just saying, for the group, can you use arrows or do you have to say imply?
Well, that's what this arrow means. So the double arrow like this means implies. Yeah. And you will see lots of that people use this. Right?
I have a question.
Yeah.
So this proof only works if epsilon is positive, but what if it's negative?
Epsilon is never negative. Epsilon is always positive.
Okay, thank you.
Welcome. We can do one more. So I think it would be worthwhile for us to we'll do more. Actually, we're going to do a lot more, but we're going to do some nonlinear ones, and they're going to have a slightly different flavor. So let's look at some nonlinear, and if we want to at the end, we can definitely do more of these linear ones. Let's look at something like this. We want to prove that the limit as x approaches, I want to use different numbers here, kind of, yeah. No, I don't really. Limit as x approaches 2 of x squared is equal to 4. Again, something I think we're all pretty sure of, right? Like none of us feel like it's not equal to 4. Yeah. And that door handle is definitely a little wonky there.
Yeah, I'm gonna fix fix it. if
Sure,
it's-
that's totally fine. Yeah, you're good.
Okay.
Yeah. Hopefully it's not, I say it before I know if it's really gonna be super loud or not. Oh, well, we'll be all right. So not surprising, this limit's 4, right? As x is closer to 2, x squared gets closer and closer to 4. You can plug in a whole bunch of values like 2, 2.01, et cetera, et cetera. Well, not 2, actually. So here's what we're doing. Just like before, we're trying to show that if the x values, if the x values are close to 2, the y values are close to 4. Let's draw a picture. I'm going to try and draw this so it doesn't look too terrible. That's a decent looking parabola. So here's 2. Let's be careful here. So here's the idea. We want to be within epsilon of 4, right? You're always starting with the condition on y, or like the condition on your limit. We want to be within so much of your limit. And then you're going to ask, what do we need to be within of x to get that to happen? So we want to be within epsilon of our limit. I'm going to try and draw this so it looks good. I will also point out, in case you didn't know, I'm really using the notes Grant has already posted. Sometimes I'm changing it a little bit, but if you want to see nicer pictures, Grant has drawn some very nice pictures. They're available on his website. Also, another point that I wanted to point out is some people ask for like extra problems to work on, like outside of class. There's a whole bunch of problem solvings that are also on Grant's website, but I've also printed them out here. If you want to take any of them, you're perfectly welcome to. And there are solutions to them posted on Grant's website. So if you're looking for extra problems that have like solutions you can look at to see if you've done it right, it's a good resource. So we're going epsilon in either direction from 4. So here we got 4 plus epsilon, here we got 4 minus epsilon. And now if we look, and good, I've drawn this accurately enough that you can totally see that the delta to the left and to the right are not the same amount. They totally are if it's linear, right? Because when it's linear, every equal change in y corresponds to the same change in x, right? If you go up so much, you're going to go over so much. If you go down so much, you're going to go over so much. But here, right, going up this much only corresponds to a smaller change in delta because it's steeper over here. Whereas going down this much, we have a larger change in the x value because it's less steep there. So typically when you can see that the values of delta are different on either side, which is almost always going to be the case for a non-linear limit, we usually do something like call one of them delta 1 and one of them delta 2. Okay. So when we have different values, we want to pick the delta. What delta do we want to pick? Do we want to pick the smaller delta or the bigger delta? Let's look at the pictures. Let me see if I can draw this nicely. So yeah, we'll do this here. So let's say we pick the bigger delta. Again, I'm trying to, let's try and be careful here. Cool. So delta 1's the bigger delta, right? And so here's my limit. Here's my limit plus epsilon. Here's my limit minus epsilon. Now check this out. Oh, sure. Grant's website. I'll put that in the chat in a second. But you can definitely find it. I've linked to it on Canvas. You can find it in the first module, but I will also throw a link in the chat before class ends. So if we decide to go delta 1 on either side, well, then we're going to end up over here, right? That's delta 1. And so if we do that, look what happens. We end up outside of the range we actually want, right? If our x values are within the larger delta value of what x is approaching, in this case 2, then our y values end up outside of the prescribed limit plus epsilon or limit minus epsilon. So we never want to pick the larger of the deltas. We always want to pick the smaller of the deltas because that will keep us in the Y range we want. What do I mean? Draw this picture one more time. Nice. So, and again, if I pick 2, and be accurate. Pictures don't always need to be accurate, but they really do need to be accurate for this kind of thing. So instead, if we pick delta 1, sorry, delta 2, apologies. We go delta 2 to either side, then we're totally going to be safe because we're going to be here. This is going to get me up to there. Right? We're going to end up in this smaller, where we're still within the limit plus epsilon and the limit minus epsilon. So, long story, much shorter, we're always going to choose delta to be the minimum of delta 1 and delta 2. If you have 2 different values, possible values for delta, you always pick the smaller one because it's going to give you less room to work with, which is what we want. Right? We want to make sure we are within the epsilon of our limits, not outside of it. So here's what I will say, and this happens a lot. When you're thinking about things graphically, you essentially always want to pick the side that's steeper. Because the side that's steeper is going to give you less x movement for the same amount of y movement. So knowing that this graph gets steeper as we go further and further to the right, I know I should be picking this side, not this side. Now, you won't always have a good idea of what the graph looks like. Right? Some of the graphs are really easy, like x squared, we know what x squared looks like. But you might have something really, really complicated where it's really not immediately clear just from thinking about what it looks like if it's steeper somewhere versus somewhere else. So we've got ways of dealing with that as well, which we'll talk about here. So here's what we need for the proof. I still want that? I kind of want that. That's all right. Well, this is where writing both things down at the same time actually becomes really, really necessary. So we know that we want, well, again, we're trying to prove the limit as x approaches 2 of x squared equals 4. So we want both the difference between x and 2 to be less than delta, and we want the difference between x squared and 4 to be less than epsilon. Okay, so let's work on this one first. So x squared minus 4 is between positive epsilon and negative epsilon. Or what we saw graphically, x squared is less than, how do I want to write this down? 4 plus epsilon and 4 minus epsilon. Right? If you look back to what we started with here, that's really what we were looking at. We were talking about a function x squared being within 4 plus epsilon and 4 minus epsilon. And then we can solve for x. And we do know that x needs to be positive, so then we can worry about like a plus or minus a square root.
For the first part, is it supposed to be x squared minus 2?
No, it is x minus 2. Can I ask you to put your mask back on your face, sir? Thank you. Yes, it should be x minus 2 because again, right, we're looking at this. We're trying to say that as x gets closer and closer to 2, so the difference between x and 2 is small, x squared has to get closer and closer to 4. So the difference between x squared and 4 should also be small. So we've got this. And just like before, we start by saying, well, we know we need this thing for epsilon to be true, and we're going to find the delta we need so that the thing for epsilon we want is true. Before, it was easy. We said, okay, delta is like epsilon over 5. And then if x minus whatever is less than epsilon over 5, then you get the function b minus limit b less than the epsilon you want. Here it's a little bit more work. We're thinking about the graph. So I'm going to work on this. And I know that that's going to mean x minus 2 is between delta 2 and delta 1. I'm not going to say delta and negative delta. I'm just going to write delta 1 as delta 2. It's going to be okay. You can still think of this being negative if you want. Don't give me a moment and then we'll talk about it. So I'm gonna isolate x here. I'm gonna say x is between. I'm not really, yeah. Yeah. I feel like I want a minus sign there, to be honest. I know I just said the other thing, but I was wrong. And because I'm thinking about my picture. In my picture, I definitely want x to be between 2 plus delta 2 and 2 minus delta 1. Maybe, I think maybe the minus sign got cut off there when it got copied. Okay. So now what? Now where we do kind of the weird thing, where we actually set this equal to that and this equal to that. Why are we doing that? So we can find out what delta we want. So I'm going to set 2 minus delta 1 equal to the square root of 4 minus epsilon and solve for delta. Okay, well, I'm going to add delta 1 over here, subtract square root of 4 minus epsilon over there. So delta 1 equals 2 minus the square root of 4 minus epsilon. Not particularly nice. Or 2 plus, oops, gosh, these red pens, I'm so disappointed that they're not living up to there. 2 plus delta 2 equals the square root of 4 plus epsilon. So delta 2 equals the square root of 4 plus epsilon minus 2. Which of those is smaller? Well, this is why thinking of the graph is nice. If you think about the graph, and we were very specific, right? The delta 1 was on the left, the delta 2 was on the right. If you look back at the graph, it is really kind of clear the delta 2 is the smaller one because the graph is more vertical or steep over there than it is over there. But let's say we didn't have the graph. Well, it should be true that no matter how big we make epsilon or how small we make epsilon, the one on the right should be the small one, right? It shouldn't, picking a larger or smaller value for epsilon shouldn't change which of the deltas is the bigger one. Meaning, we could pick any value for epsilon we want to see which of those is bigger. Well, let's pick something like epsilon equal to 3.
We have a question.
Yeah, oh, sorry.
For like epsilon 1, I mean, for delta 1, I think it's 2 plus.
So the thing is, if we look back at the picture, this point here should be 2 minus delta 1 because we're going delta 1 to the left.
Okay. Okay. Yeah, I see.
Good.
Mhm.
Cool. So if we take epsilon equal to 3, we're going to get delta 1 equal to 2 minus the square root of 4 minus 3, which is 2 minus 1. And if we pick epsilon equal to 3, delta 2 is going to be the square root of 7 minus 2. Is the square root of 7 minus 2 bigger than 1 or less than 1? I think it might be smaller than 1. Right? So what's the next integer that the square root of 7 is definitely less than? Square root of 7 is less than the square root of 9, which is, oh yeah. So it is less than 1. So we see that the delta 2 is smaller than the delta 1. So that's the one we want. And we want the smaller one. So that's the whole point, is if you can't tell, or if you didn't know what the graph looked like, you can also just pick a value of epsilon and try and figure out which of these two things is the smaller. And it should always work, right? You can pick a totally different number. Now you can't go too far. Like if you pick epsilon equal to 5, you're gonna run into problems because you have the square root of the negative, but okay. So now the proof. The proof is actually not terrible, believe it or not. We've done all the work. So here's our proof. For any epsilon greater than 0, we can see that if delta is equal to the thing we just found, the square root of 4 plus epsilon minus 2, then it is true that x minus 2 in absolute value less than delta is going to give us that f of x minus the limit is less than epsilon. Thus, the limit as x approaches 2 of x squared equals 4. Now, if I were submitting this work somewhere, not on web work, obviously, but like if I was asked to write something up, I would definitely include some of what I've written up here, right? If you just wrote this, someone might be like, how the heck did they come up with those numbers? So you really do want to show what I would say this whole page is my quote unquote scratch work. And this is my nice proof at the end. And this is the way the textbook does it. It is possible, although I feel like it's probably less likely. So there are some, there's very few of them. There are some teachers still on campus that were here when I was a student many years ago. And they definitely, back then, taught these limits a slightly different way. More than slightly, actually, kind of a very different way. Still correct, still accurate, but just different. I don't think we need to cover that unless you're specifically telling me we need to. So there's another way of doing this where you pick delta to be the minimum of some just random number and some other thing. And it's very it's not the same as a spell. You don't really look at the graph. It's kind of very arbitrary. I think this method, the way this book does it, is better. So I think we should definitely stick with this. But if you tell me your teacher is doing something different, they're referring maybe to an older textbook. If you don't think anyone's been here that long. So you shouldn't see the old stuff. I'm just gonna leave it at that. There's another way of doing this. I don't think we need to cover it. But if you tell me your teacher is doing something that's different from what the book is doing in this regard, we will talk about it. Let's look at another example. I know it's a lot of time spending on this Delta-Epsilon stuff, but it's kind of important. It's kind of important. If you're a math major, it's super important. If you're not a math major, it's important that you learn it to pass this test. And then it'll probably also pop back up in 21B or 21C minorly. Let's look at another example. Let's prove the following on this. Limit as x approaches 3 of 4 over x plus 1 equals 1. And I think it would be in our benefit here to actually not draw the picture. I think it's always to your benefit to draw the picture. Let's try doing it without the picture so we can see how to attack what it is without actually having the graphical information for us. Here's what we know we need. X is approaching 3, so we need the difference between x and 3 to be small. And the function should be getting closer and closer to the limit value of 1. So we also need that the absolute value of 4 over x plus 1 minus the limit is less than 1. Sorry, epsilon. Gosh, why does my brain want to say the wrong thing so many times? This is a reminder. All the things I've written say, this just says x is close to 3. This just says f of x equal to 4 over x plus 1 is close to 1. That is all those things are actually saying. And as usual, we're going to work on this one. So in this case, it's not the same as the line ones, right? We're not doing a bunch of algebra. I mean, we are doing a bunch of algebra. We're not doing something that we're like solving. We're not going to get x minus 3 showing up. We're essentially going to work on both of these until we just get x by itself. So if it's nonlinear, you're going to work with both of these inequalities until you just get x. This one's easy, right? This one, x minus 3 less than delta, bigger than delta. Oh, sorry, here's where you want to do the, I really think it's you want to do less than delta 2, bigger than negative delta 1. I think that's going to be the smarter way to do it. And then you're going to add 3 to both sides. because you're thinking of both deltas being positive. So you're going to be 3 less a positive number to the left, 3 plus a positive number to the right. Okay, this side is going to be the side that's a little bit more effort. So I've got 4 over x plus 1 minus 1 between epsilon and negative epsilon. And then we have to get x by itself. So I'm going to add 1 to every side. So 1 minus epsilon less than 4 divided by x plus 1 less than epsilon plus 1. Or 1 plus epsilon is probably what I should write to keep it kind of similar. And then I need to get x in the numerator. I don't really want to multiply everything by x plus 1 because I'm going to get x plus 1s out here and I really need to keep x in the middle. So what should I do instead? Right. But if I reciprocate, what else do I have to do? Oops, I actually need to do the reciprocal maybe. I'm running out of room. I'm right over here. So if I do the reciprocal, x plus 1 over 4, I have to do the reciprocal to the other sides as well. But what else changes? Right, the direction changes. And then we need to isolate x. I'm going to multiply everything by 4. So I'm going to have 4 over 1 minus epsilon bigger than x plus 1 bigger than 4 over. I'm going to write that as 1 plus epsilon in the bottom. And then finally, I'm going to subtract 1 from every side. So 4 over 1 minus epsilon minus 1 bigger than x bigger than 4 over 1 plus epsilon minus 1. Or as I would probably write this, so x is between those two things. And we also have the other condition. X is between 3 plus delta 2 and 3 minus delta 1. And oh yeah, sorry. Yeah. And so then this is where things, continue to get gross. We're going to set these equal to each other and these equal to each other. Now, this is a time where I wish I had done the graph because I'd really like to know which one of these is going to be smaller without having to check both of them. I'm still going to do the work because I think it's worth seeing for you all, but right, it's going to be easier if you use the graph, or at least if you think about the graph. So we'll do this, but then we're going to talk about the graph. So let's see. Okay, so 3. It's not okay. It's not as bad as I'm making out to be. Solving for delta 2 here is not hard. 3 plus delta 2 equals 4 over 1 minus epsilon minus 1. Subtract 3. Delta 2 is 4 over 1 minus epsilon minus 4. Versus delta 1. 3 minus delta 1 equals 4 over 1 plus epsilon minus 1. Bring the delta 1 over there and the other stuff over there. So you get delta 1 equal to 3 plus 1 is 4 minus 4 over 1 plus epsilon. So which of these is smaller? So we need to pick a value for epsilon. We need to be careful because if you go further than 1, you're going to have problems, right? If epsilon is 1, you're going to get division by 0. And if epsilon is bigger than 1, you're kind of getting into a weird place. So we need to pick, you need to still think about picking an epsilon that's relatively small. Without any other guidance, I would probably pick epsilon equal to 1/2. That seems like a safe choice to me. So I pick epsilon equal to 1/2. I get delta 2 equal to 4 divided by 1/2 minus 4, which is 8 minus 4, which is 4. I get delta 1 equal to 4 minus 4 over 1 plus 1/2, which is 3/2. 4 minus 4 over 3/2 is 8/3. 4 minus 8/3 is definitely smaller than 4. So delta 1 is the 1. It seemed like a lot of work. Maybe not a lot, but I don't want to have to do this. So here's what I would point out. The graph of y equals 4x plus 1 is not that hard to do. got a vertical asymptote at -1. It has got a y-intercept at 4. And then it looks like this. And I'm just going to say, no matter what point I pick over here, we're picking 3 because that's what x is getting close to. But no matter what point I pick over here, let me ask you all. Is this thing steeper on the left side of 3 or the right side of 3? I know my picture's not great. It's definitely steeper on the left. That's the side you want. The steeper side is the side that's going to have less x for the same amount of y. So we know that over here at 3 minus delta 1 versus over here at 3 plus delta 2, right, that's going to be the side we want, because that's going to give us the lesser amount of x. And that's what we got, right? We got the delta 1 one. So we're convinced, I hope, that that's what we want. If you want to see a better picture, here's a better picture for you. So we can see here's our 4 over x plus 1. And if we look at 3 here, and the limit value being 1, we go the same amount up or down, you can see, oh yeah, this up part corresponds to here. This down part corresponds to way over there. You're getting a lot more play there than you are getting there, because it's steeper here than it is there. So we could have not done the work of dealing with delta 2 because we already knew it was going to be delta 1. That's what I'm trying to say. So if you can think about what the graph looks like with relative ease, you can not have to look at both of these. Just be like, oh yeah, I know it's the one to the left, I know it's the one to the right, and then just solve what that's going to be. And then the proof after we've done all this is not too terrible. We know that if x minus 3 is less than this delta 1, right? So in fact, let me just point out that Grant is a much better picture drawer than me. But let me just point out, if we're within this delta 1 amount, and if we go that much to the left or that much to the right, we're definitely going to be within epsilon of our limit, right? We're going to end up living in there, which is totally in the prescribed range. So we're just going to write the words that say that. It's not a lot to write, actually. Here's our proof. You can say, great. That's an interesting way of writing it. So for any epsilon greater than 0, if delta is equal to, I forgot what it was, it's right there. It's 4 minus 4 over 1 plus epsilon. Then the absolute value of x minus 3 less than delta implies that the absolute value of, I don't like to write f of x minus L, but some people do. I would actually like to write the function, which was.
Can you move it up?
Oh yeah, of course. Thank you. Yeah, I know. There's that spot there. I could not be on camera if you guys would prefer, but I feel like it's weird later. So, but if you really, really don't want to see my face, that's also perfectly fine. Sorry, I forgot what the function was. Let's look back. The function is 4 over x plus 1 minus the limit, which was 1 is less than epsilon. Right, that's literally the work we just did. Because remember, how did we end up with this condition that delta 1 was equal to that and delta 2 is equal to that? Well, we started with this has to be true and this has to be true, which is what we're saying is true. All we did was start with this. We solved for x or we isolated x in each of the inequalities and then set the right side and the left side equal to each other. So really, right, what we're doing here is we're saying, oh yeah, these things are true because that's the work we did. We found the things that made that true. I will also point out that if I was a teacher and just saw this, I'd be like, where's all the work they did? I have no idea how they got there. Like, I'd be like, oh, it's right. Did they look it up somewhere or did they do the work? So if you're actually doing a Delta-Epsilon proof and you're submitting work like on Gradescope or something, I would encourage you to show your work. I didn't get 1/2 for epsilon. Yeah, so I didn't have any particular value for epsilon here. Are you talking about a previous question? So yeah, so right, we were proving this limit, and we just kind of started with, or is it what? Yeah, we got a 1 over epsilon. So right from here, I isolated the x and got that, and from here, right, I did a lot. So right, it's a lot of steps. We wrote less than epsilon, bigger than negative epsilon. We added 1 to both sides, and got that, and then we took the reciprocal. Oh, yeah, sorry. I know my work's a little kind of out of order here. We then took the reciprocal of both sides and got 1 over 1 minus epsilon is bigger than x plus 1 over 4 is bigger than 1 over epsilon plus 1. And then we multiplied everything by 4. Then we subtracted 1 from everything. Then we changed the direction of the inequalities just to see it better. Yeah, so it's not a 1 over epsilon so much, it's a 1 over epsilon plus 1, and then it's finally a 4 over 1 minus epsilon minus 1. Or really it's a 4. This is our actual, well, try, I mean, it's a lot of work. So what we did then, we said this and this have to be the same, and then we solved for delta 1. And finally, setting that equal to that, we got delta 1 equal to 3 plus 1 minus 4 over 1 plus epsilon. Your deltas are not going to be pretty for these nonlinear ones. Like the previous example was a little nicer than this one, but this one's kind of exceptionally gross. They're all doable though, right? You can take these two inequalities and always solve each of them for x. I'm trying to think, like, probably. There might be some weird exceptions. I don't think there's any weird exceptions, really. Or at least your teachers shouldn't be assigning any weird exceptions, really, is what I want to say. And I don't think they will. Sorry, I think you gotta. There's a thing I just saw there. Okay. So I use 4 divide. So I don't see where there's a 1/2. And there's no 1/2 that I'm seeing anywhere. Okay, I take it back. I mean, yes, it's like I don't see it, so not like the page. So what I was talking about right there was I was saying if epsilon, sorry, I see your question now. I apologize. We were trying to do it without the graph before. And we were saying, well, if epsilon was equal to 1/2, then the delta 1 value would be smaller. So it's not that we were specifically saying epsilon is 1/2. We were using that to determine whether delta 1 or delta 2 was the bigger value or the smaller value. And then we said, alternatively, more easily, we can just look at the graph to see whether it's going to be smaller to the left or smaller to the right. That's what's going on there. Sorry, I totally didn't get your question, but your question was very apt and I was just missing it. Other questions about this?
Just in general, what the point of a delta epsilon proof is, at least if it's continuous, like to prove it, could you not just say that the function is continuous? So if you plug it in, then that's the limit.
So, not wrong. It is totally true that if a function is continuous at a point, then the limit is whatever the function value is. And that's kind of a result of what's the substitution property. And for continuous functions, or functions are even less so. They don't have to actually be continuous. They have to be continuous on their domains, like tangent or something like that. It's not defined everywhere. A function is definitely continuous at something. The problem is to prove a function is continuous at a point, you actually have to show that the limit exists. So you don't get the limit existing from continuity. You get continuity from the limit existing. But I will still say this, you would never do this to prove a function is continuous somewhere. The only reason we are really doing this is to really kind of drive down into the details of why a limit is what it is. And again, what we're really saying with a lot of words and a lot of symbols, we're really just saying that if x is close to some number, the function is close to its limit. That's all this giant mess is really getting at, right? This is really just saying if x is close to 3, well, how close does it have to be? It has to be this close. Then f of x is close to its limit, this close. So you can make up a number, right? You could say, well, what if epsilon was 1/100th? Well, then I don't want to do the math, but you could say, well, if epsilon was 1/100th, then delta would be 4 minus 4 over 1 plus 1/100th, which would be weird. It'd be fine. It'd be a very small number. It'd be 4 minus almost 4. And then you would end up getting that the function was within 1/100th of its limit L. Because the real kind of detail here that I'm kind of, I don't want to say I'm avoiding, but I'm not saying so much is that the whole point is that you can actually make things as close as you want to. So it's not just that you can get specifically close, you can always get x closer and closer and closer and closer and closer and closer and closer to, in this case, 3, and end up getting the function value closer and closer and closer to 1. As close as you want. That's the whole point. Well, other questions. So I know we spent the whole day talking about essentially this. Before we leave, because we still got 7 minutes, I should briefly, I think, well, I mean, there's a lot of different things we can talk about, but continuity is kind of the next big thing that's coming up for most of you. Okay, yeah, if you in general, if you need to leave early, you can just leave. You really don't need to tell me. I'm not like, it's not that I don't care. I like you all, you're all welcome here, but I'm not in charge of policing your behavior. So, and not that I'm saying it's bad behavior, I'm just saying, like, I'm not in charge of you. Do whatever you want. If you gotta go, go. Right. So, continuity. There's definitely still a lot of different limits we could talk about. I'll squeeze them too. There's never enough time. Okay, so we'll talk about continuity. I just want to say things about continuity. To show a function is continuous at a point, typically the point a comma f of a. We usually do this in 3 steps. Although I will point out, it's really just one thing we're showing. The first 2 things are just part of the third thing, but it's usually easier if we break them up into 3 equal pieces, or 3 separate parts. So the first thing you need to show is, you need to show that f of a exists. Usually this just amounts to plugging in whatever a is and see if you get a real number or not. The second thing we need to show is we need to show that the limit as x approaches a of f of x exists. And then the third thing, which really encompasses the first 2 things, is that they have to equal each other. So typically, the definition of continuity at a point is just written as this third thing, where we correctly assume that for these to be equal, they both have to exist. And if the limit didn't exist and the function didn't exist, you wouldn't say that they were equal to each other because they both didn't exist. Right? That would be wrong. So we need them to both exist and they have to be the same. So a couple of non-examples. So f of x equal to, say, I don't know. Oh, there's a good example, James. Sure. 1 over x minus 2 is definitely not continuous at x equal to 2. It's not defined there. F of 2 does not exist. End of story. We don't need to do anything else. It's also true the limit doesn't exist, but okay. Here's another example. Here's an example back to the beginning of class. F of x equal to the square root of 5x times x minus 3 over the absolute value of x minus 3. Oh, that's still not a great example, James. Fine. I'll make it piecewise. Even make it interesting. Make it the square root of 15. Oh, that's not what I meant to do. This function is not continuous at 3. Why not? Well, is the function defined there? Well, it actually is, right? Because we made it a piecewise function. If it was just that, I'd say, yeah, for sure. Not continuous because it doesn't exist at 3. But we then added on a piece. We said, oh, okay, we're going to try and make it work. We're going to say that f of 3 is the square root of 15. It's not continuous, not because it doesn't exist, because it does, but because the limit as x approaches 3 of f of x does not exist. We showed in the beginning of the class that this limit does not exist because the left-hand side and the right-hand side weren't matching up. So that's another way a function cannot be continuous, if the limit doesn't exist. Often the limit doesn't exist because the left-hand side and the right-hand side aren't doing the same thing. I mean, those really itches. Okay. And then kind of the way that's the most disappointing way a function cannot be continuous is when the limit exists and the function exists, but they're not the same. Kind of the nicest example of this is f of x. Well, nicest is, I'm going to say is sine of x over x when x is not 0 and 2 when x is 0. So the function exists. F of 0 is definitely 2. The limit also exists, and we'll talk about this next class. The limit as x goes to 0 of sine of x over x is what? 1. It's a very nice geometric proof of this. For now, what I'll say is, yeah, I got a minute. If you look at that graph, you can totally see, oh yeah, as the x values are getting closer and closer to 0, the y values certainly seem to be getting closer and closer to 1, but at 0, it's undefined. So there's some graphical evidence that the limit is 1. It's not a proof, but it's very good evidence. But disappointingly, the limit as x approaches 0 of this function does not equal, sorry, the brain always forgets about that. Oops, come on. The limit is not equal to the function value. And graphically, you can also, right, if I draw that same graph, which kind of looks like, you know, that, something like that, but then I've got this point up here, right, you can see that I can't draw the thing without lifting my pen off the paper, right? I've got to do this, and then this, and then, oh, got to go up there, and then back down there. So definitely not continuous. It's not continuous at x equal to 0. And these are kind of the 3 different flavors of discontinuity. You can be not continuous because you're not defined. You can be not continuous because your limit doesn't exist. Or you can be not continuous because the limit exists and the function exists, but they're not the same. Those are the 3 kind of different ways. So for a function to be continuous to the point, you need the limit to exist, you need the function to exist, and you need them to be equal to each other.